Hello everybody, welcome back to this video on neural networks and deep learning. In today's video, we are going to talk about gradient descent algorithm. In fact, what we will do is a very mild and gentle introduction into the concept of gradient descent so that later on when we talk about gradient descent in the context of neural networks, it's far easier for us to understand the concepts. If I look at the structure of a feed-forward neural network, I'm assuming that by now you will be familiar with this kind of a structure because we have talked about it in few of our previous videos as well. So this is typically how a feed-forward neural network would look like, right? So there will be far in the far left hand side there will be the input features. They will be fed into the first layer, which is the hidden layer, which will have some neurons. In this case there are three, there can be more, and each neuron will actually do a linear combination, a weighted linear combination of the input features, apply an activation function, and then pass on the signal for the subsequent hidden layer. In this example, I'm considering two hidden layers and three neurons in each of them. And finally, we will have the output neuron or the output layer neuron, whichever way we may call it. The output layer neuron gives us the final decision. And in each of these neurons, we are also applying the activation function on the weighted combination of the inputs which are coming to this neuron. So in this kind of a structure, I kept talking about weighted combination, right? So every connection here has some weights associated with it. So training a neural network is nothing but is the task of estimating these weights. Now, how do we estimate these weights? So that's the question out here. Now, before trying to answer that question, how do we estimate the weights? Let's think about linear regression problem, plain vanilla linear regression, right? In linear regression, how do we estimate the weights? We try to estimate the weights such that the error committed by the regression model is minimized. And in the context of regression, the error is nothing but the deviation, the square of the deviations between the actual values of the target variable and the predictions made by the model. So we look at a squared error deviance in the context of regression, and we also call it the error function or the loss function, and we try to estimate the weights in such a way such that the error function or the loss function is minimized. It's a far easier problem to solve in the context of regression. Now, in the context of neural network as well, we do the same thing. So we have the output decision coming in from the output layer of the final neuron, and this being a supervised learning problem, we have the actual values of the target variable. So we define some kind of a loss function here. So it can be a square error loss function or it can be any other form of loss function, but we define some kind of loss function or the error function which in some way quantifies the difference or the deviance between the decisions given by the neural network and the actual values of y, and we try to estimate the weights of the neural network in such a way such that the loss function or the error function is minimized. So we try to minimize the loss function and we want to get the weights which does this minimization. So very similar concept to that of regression, the same thing that we do in neural network, just that for neural network the problem of obtaining the weights such that the error function is minimized is not at all straightforward as it is in the case of linear regression. So One of the algorithms which is very popularly used in the context of neural network for estimating the weights or minimizing the error is called gradient descent. Now, before we go into discussing how gradient descent actually comes into the picture when it comes to neural network, we will do a gentle introduction to to gradient descent, because otherwise, some of the mathematics involved in the gradient descent for neural network can be quite overwhelming, and it is not friendly at all. So let us first do a very basic introduction to gradient descent, and I would call it a geometric interpretation of gradient descent, which is far easier to visualize. So think of a simple function f that we want to minimize, and it's a function of a single variable x, and let's assume that f is a very decent looking convex function which we would always be able to find a minimum of, right? So let's start off with a very simple example like this. So if I plot this, let's say it's a convex function and xm is the minimum value of f. Now, the objective of my algorithm will be to arrive at xm, right? I can always calculate the derivative, equate the derivatives to zero, and find the minimum value uh, by calculating the second order derivatives, because this is a convex function. But let's assume that let's for a moment think that it's not the algorithm that we are going to try out here, because if you do not have a closed form, if you do not have a closed form expression from the derivatives, it will not be so straightforward to equate them to zero and solve them as a system of equations. So in such cases, how do we estimate the minimum value? So what we do is we start off with a random choice or a random guess of the minimum value. And that random value, random guess can be anything. It can be significantly different from what the actual minimum value is, and it will be the case in most cases. So let's say our initial random guess is x naught, and let us assume that this is where x naught lies on the x-axis, and this is what the value of fx naught is. So our objective will be, based on this random initialized value of the minimum x naught, we will try to run some iterations in such a way so that each iteration takes this value x naught closer to the actual minimum value xm. So we have to sort of do something, some mathematical operation which moves x naught closer to xm. So let's see how we can do that. So let's say this is the point where we made the initial guess x naught. So let us compute the gradient or the derivative of the function f at this point x naught, and that is nothing but the tangent, the blue line, the tangent which is showing up here. So it is very intuitive from this diagram itself that if I have to move x naught in the direction of the desired solution xm, what should be the magnitude of the movement? The magnitude of the movement should be proportional to the magnitude of the gradient of this function f at this point x naught, right? Because this is the tangent, and at x naught, if I calculate the value of the gradient of the function f, or the derivative of the function f at x naught, and I add that magnitude to x naught, definitely x naught will move some distance towards xm, right? Let's say x naught moves to x1, which is closer to xm than x naught was. Then what I can do is I can again calculate the derivative of the function f at the point x1 and calculate the gradient there. and then using that value of that gradient, I can further move x1 in the direction of xm. So that will take x1 more towards xm, and like this iteratively we can keep moving the initial choice x naught towards the desired value xm, and for each such movement of x we calculate the error or the loss function which I was talking of previously. When we stop when we see that a further update of x does not improve the error or does not improve the loss function, which means that I have arrived at the minimum, right? So that is when I stop, and and I can starting off with any initial choice of x naught using the gradient descent algorithm, I can make these small movements and move towards the desired value or the minimum value, right? Now, having said so, there are some other factors to be considered here as well. So we'll look at those factors. So as of now, our algorithm for gradient descent stands pretty much like this. We start off with a initial random guess value x naught, and then at x naught we calculate the gradient, and we add the value of the gradient to x naught and move it more closer to xm. So uh, and this we keep doing this iteratively. So if we sort of write this in a generic form, at the k plus 1th step of the iteration, xk plus 1 should be nothing but the previous value of x in the iteration stage xk plus whatever is the magnitude of the gradient of the function f at x equal to xk. So this is how we keep on updating the value of x. Now, and it's also fairly obvious that the initial choice of x that we were making x naught, that can also be on the right hand side of xm. It need not always be on the left hand side of xm. So if it is on the right hand side of xm, then obviously the magnitude of the gradient will still continue to be the same, but the sign will be the opposite, and hence we will be again in that case subtracting something from x naught and bringing it closer to xm. So it's that part is fairly obvious. So the initial choice, if it is to the left of xm, then the gradient is positive, and we add something to x naught to make it closer to xm, and vice versa if x naught is to the right of the desired solution xm. So this is how the iterations work. But there is another nuance to look at in the context of gradient descent, and we will look at that nuance now. So basically, I can also represent the iterations that I am doing by these loops. So these are the small steps, the baby steps the initial choice of x naught is taking in its journey towards the final value xm. And how are we by what extent, even though I'm calling them baby steps, but it can be giant steps as well depending on the size of the gradient. So by what extent x naught is shifting? It is shifting by the value equivalent to the gradient that we are calculating. So the problem is, do we really want to shift the value of x at that particular stage of the iteration by something which is equivalent to the gradient, or something which is a fraction of the gradient? Because if we shift it by something which is equivalent to the gradient, then it is very likely that while we are taking these steps, we at a certain stage we can miss xm and go to the other side of xm, right? Because the the updations or the iterations that we are doing is these are pretty much like step functions. So and these are jumps that we are making. So it can well happen that I skip xm and I move to the other side of xm, and then I keep moving in the other direction. So that will be a problem, right? The iteration will never then converge to the desired value xm. That is why when we are updating the x values at every iteration, instead of taking the gradient of fx, we actually take some small fraction of the gradient of fx. So this value eta, this is often called the learning rate in the context of neural network, and we can make a choice of this between 0 and 1, typically between 0 and 1. So if we take very small values closer to 0, then whatever be the size of the gradient, we will be taking very small steps, baby steps towards the desired value. That way the convergence time will be a lot more, but it will be ensured that we will not skip the desired value and go to the other side. However, if we take a very large value of eta, something which is very close to 1, then obviously the steps will be larger. Convergence will, if it happens, will be quicker, but then there is always a risk that we can skip xm and go to the other side of the curve. So the optimal choice of eta, it's basically, there's no rule for that, but we have to try different options and see how the errors change for different choices of eta, which is called the learning rate in the context of neural network. So this is how gradient descent works. So this is basically the geometry of gradient descent that I'm talking of. In the context of neural network, things are not so simple. Why things are not so simple? Number one, in neural network, the error function that we are talking of, it's not a univariate function. It's a function of all the weights that I have introduced in the neural networks. It's a very high dimensional function. So uh, its representation will be some kind of a surface in higher dimensions, right? And also, it is not likely to be a convex function like this, where you will have a global minima point or a universal minima point. So even in the high dimension in the surface, which will be which will be the representation of the error function of neural networks, even in that high dimensional surface, if we run gradient descent and whatever value of learning rate we may choose, and we start off with a random initial value, and then we take baby steps and try and move towards the minimum value. Whatever minimum value we reach at, that there is always a possibility that that minimum value is a local minima and it is not a global minima. So so that can still happen. And there are ways to take care of that. I'm not going into those nitty-gritties for the sake of simplicity now, but the message that I want to drive home is, when it comes to gradient descent, this is the geometry of gradient descent, and this is a very clear interpretation of how the algorithm works. In terms of concept, it's the same concept which is applied for neural nets, but things are not as simple as we have seen in this toy example out here. So in the next video, we will look at how gradient descent is applied in the context of a neural network to do the error minimization and the weights estimation of the network. So that's it for this video. Thank you for watching, and stay tuned for more videos to come. Thank you.